Okay, so thank you for inviting me to give this presentation. I'm going to talk about two different models, central versus local models to assess long-term exposure for the ELAPSE project. And what I'm going to do in this presentation is explain what the central and local exposure models are and make some comparison between those models. And what I'm not going to do is show any epidemiological analysis with these two types of models simply because of the fact that we haven't done them yet. So rather than making up results, which is popular in some places, I will do that next year in the conference in Utrecht. I could give you the prior. I could give a fake result or something. Okay, so first of all, what is ELAPSE? ELAPSE is one of the projects funded by the Health Effects Institute to look at health effects of low-level air pollution. So air pollution below current air quality guidelines in okay, I was pointed that I could look there as well. Good. This study will look at mortality, lung cancer incidence, and cardiovascular events as the health outcomes. And we have two sets of cohorts. One selection of cohorts with individual level confounder data, largely from ESCAPE, but supplemented with the Danish nurses cohort, covering in total 380,000 subjects. And this is analyzed as a pooled cohort. So we don't analyze individual cohorts, we pool them together and analyze them. So, which is different from what we did in ESCAPE, where we used individual analysis and then meta-analyzed it. And then in addition, we have 7 administrative cohorts in England, Norway, Denmark, Italy, the Netherlands, Switzerland, and Belgium. And that adds 27 million subjects to the analysis, subjects older than 30 years old. And they are analyzed individually, and that's because of privacy regulations. They're not allowed to send data outside. They have to do it in their own institute. This shows the distribution across Europe. The open circles are the individual level cohorts. So they range from Sweden, Norway to Italy. As you notice, the south of Europe is not included in this, and that's because there are no low-level PM concentrations there. And this is a low-level air pollution project. The blue shaded areas, those are the administrative cohorts. So you see Norway, England, the Netherlands, Belgium, Switzerland. So most of them are national cohorts, with the exception of the Rome cohort, which has been published previously. Okay, so what's the central exposure assessment? That's a Europe-wide model, or the part of Europe which is covered by the cohorts. Why did we go to this effort? Because we already had land use regression model from the ESCAPE study. There we did develop models per study area, but that was based on a small number of monitoring locations, typically no more than 40 locations. So we really wanted to have more robust models developed on larger number of sites, so that's one reason to do that. The other reason is that the ESCAPE models were limited to the study area of the cohort, and applying a Copenhagen model to all of Denmark did not seem to be a good idea. So we wanted to go to larger area models. The models were developed based on routine monitoring data for PM2.5, NO2 and ozone, and on ESCAPE data for black carbon, because there are no consistent data on black carbon across Europe. This shows you the map of the sites across Europe. So the two top ones are PM2.5 and NO2 from routine monitoring, well spread over Europe. And for PM2.5 in the year 2010, where we developed models, there were about 500 sites, and for NO2 and ozone, about 2,000 sites available to develop the models. And in the right bottom is the model for the monitoring site for ESCAPE. There were about 400 sites available. That's not the impression that this gives, but the sites were linked with, concentrated in local study areas. So most of the dots actually represent 20 to 40 sites, which you don't see on the European scale. But there are also 400 sites, so a sizable number. Now, briefly, what the central exposure assessment method was. We went to 100 by 100 meter grids, so quite detailed, because we wanted to cover fine-scale spatial variation. And as predictors, we used land use, traffic, altitude, and also satellite observations of PM2.5 and NO2. And in addition, a chemical transport model, also at a large spatial scale. In addition to doing linear regression-based modeling, we also looked at whether there was still information left in the residuals of the model, and we performed kriging if that was the case. These are the land use regression models developed. So for PM2.5 and ozone, kriging contributed considerably to the prediction, which makes sense because these are regional components. And for black carbon and NO2, kriging did not contribute. That's because they are more local pollutants. In the PM2.5, so that the numbers that you see in these models are in micrograms per cubic meter, and except for the intercepts, they are expressed comparing the 99th percentile of the predictor versus the first percentile of the predictor. So you can actually compare these numbers. So if you look at PM2.5, you see that the largest predictor is the satellite PM2.5. So from the first to the 99th percentile of the satellite predictor predicts an increase of 13 micrograms per cubic meter PM2.5, which is a lot. The PM2.5 model contains only one traffic variable, the all roads variable. For black carbon and NO2, it's more mixed. There is a lot of traffic variables in the model, but in addition, the satellite and chemical transport model predict. For ozone, the chemical transport model actually took up. So that's the first one, 32 micrograms per cubic. That was the most important predictor. So they do pretty well. And the other components reflect scavenging by roads and urban areas. These are the maps which are then generated from these models, showing a large variability across Europe, both for PM2.5 and NO2. Black carbon and ozone. I'm not going in detail to have some time to look at the comparison. So that's about the central exposure assessment. This is the local exposure models, and it defines for the different pollutants what local exposure models were available. So it's land use regression models from ESCAPE, so study area specific models for the pooled cohort, and then for the Dutch and the Rome cohort, which were involved in ESCAPE. We also have the land use regression model from ESCAPE for them available. But for all the other cohorts, we didn't have that available, and people used dispersion models for the local models. But what you notice, if you look, for example, at the PM2.5 column, they're all different. Every country has its own model, so that raises some challenges in terms of comparing results. Okay, comparing the local model with the central model for the pooled cohort. For the first thing to notice in this table is that for the central model, we were actually able to get exposure estimates for about 50% more people than from the local model. And local here is the local ESCAPE model. And that's because the central model can be applied to more areas. For PM2.5, the correlation between the central site and the central model and the local model was actually pretty high, 0.81. For NO2, the correlation was lower, and that was mainly reflecting the description of differences between cohorts. Now I want to show something which relates to whether to use a central or local model. So overall, we explained quite a large fraction of the variability across Europe. So for PM2.5, overall 65% of the spatial variability was explained by the model. But when you evaluate, and this is holdout validation R-square, but when you compare this in a smaller area, like in the Dutch cohort, the English cohort, or the Rome cohort, then these R-squares get a lot smaller. Actually, within the Netherlands and the English cohort, they explain very little of the variability. So this is one issue that, on the one hand, it's great to have a national model, but if you apply that national model to a smaller sub-area in that model, it doesn't necessarily perform as well. And for NO2, you see in the bottom part of the column that's much less the case. There, the model performs in most of the areas quite well, with the exception of the Swiss centers where the model performs really lousy. Some of this may be due to relatively small number of sites, because of course when you zoom into a sub-area it becomes smaller. And the other part that may explain this is the root mean square error. But if you focus on PM2.5, you note that while the R-square is really low for the Netherlands, the root mean square error is just 1.7 microgram per cubic meter. So some of this reflects the fact that there's little variability in sub-areas. But I see my time is almost up, so I'm just going to skip this. Moving to the summary. Okay, so we developed central models to be applied in epidemiological analysis. The main benefits of the central model for this project is that we can cover more areas than we previously could cover. So all of France instead of only Paris. All of Denmark instead of Copenhagen. One advantage is that for the project is that it's a harmonized model rather than using country-specific dispersion models, which are all different with different validity in the analysis, and compared to the ESCAPE, the robustment, because it's based on a larger number of sites. The performance in smaller areas was less than the overall performance, especially for PM2.5, so that may raise some issues. We noted that the correlation with local models was high for PM2.5 and more moderate for NO2. And we will apply, actually, independent of these results, both the local and central models. That's already 2 years in our protocol. And the results of that you will see next year in Utrecht when the ISEE is organized. That's it.